work by. So that's good. That's what I want the engine in my car to do. I want to provide it heat, and I want it to provide me back useful work. I want it to do the work of turning the crankshaft in my car and making the wheels turn and all that, right? So that's what engines do. What heat engines do, they take heat in, give useful work out. That means they go clockwise along some trajectory. It could have any different kind of shape. It depends on the details of what kind of engine we're talking about. We'll talk about the Carnot cycle in a few minutes, but this is just some random egg shape I just chose to draw in my hat. But in terms of the thermodynamics, like, do I get work out or do I put work in? You always get useful work out when you go in a clockwise direction. Counterclockwise is the opposite. In fact, counterclockwise is useful as well. So what do you call these things if it goes counterclockwise in the PD diagram? So what is it? What object in your house is it where you provide work, you pay for it, you pay for this useful type of energy, and it gives you back a heat pump, and it pumps heat out of what you want to pump your heat out of? Your refrigerator. So refrigerators take useful work in and give heat out. So your refrigerator's giving you heat. What does that mean? It means it's cooling off your beer or whatever you keep in the fridge. You know, so which is good, right? It cools stuff off. It might seem like a violation of second law of thermodynamics, which we're going to get to in 2 minutes, or maybe either today or tomorrow, or next week, I mean to say. But it's not a violation, and it's not a violation because in order to think about these things, we have to separate. There's usually two objects involved. Remember the heat exchange? One thing's getting heat, the other thing's losing heat. And as a result, you understand what's going on in terms of the total entropy change. You look at both objects. So I'm getting ahead of myself. So good. If we whatever shape this is, if you can calculate the area under the curve for these two shapes using those kind of tricks, and the shapes can be really easy, straight lines and whatever adiabats and different things that you're familiar with, you can then figure out what the net amount of work is produced per cycle. And that equals, for a closed circle, for a closed cycle, I should say, the heat you get out, that you put in is equal to the work you get out because the energy doesn't change. Energy is a state variable. What's the change in energy from point 1 back to point 1 again? It's got to be 0. What's the change in the temperature for the gas when you go around the cycle back to 1 again? It's got to be 0, right? It's a state variable. Temperature and energy only depend on where you are on that plot. Okay? Yeah. I think I got the signs right. I think that's correct. Yeah, absolute value. Yeah, thanks for asking. So what you're saying is, yeah, the magnitude of this area is bigger than the magnitude of that area. And that's how I know these facts combined, that combined to that, combined to that statement tells me that work on for the cycle is greater than 0. No, that's less than 0. Right? Work on is less for this cycle, which means that work by is positive. Because that's just, negative work on, right, is greater than 0. So it's an engine, right? Good. Yeah. Okay? So, and also, there won't be any refrigerators on the exam here. And there might be you might see a heat engine on the exam, and you'll see examples from past years on there, the sort of thing I expect you to do. So the canonical example of a heat engine is a Carnot cycle. Oh, here, should I do this demo? Maybe I'll do this demo and get it out of the way, literally, so you can see the board. Yeah, before I do that, so one thing I told you that PV equals NKT, and everything we're doing today is with fixed number of particles. Everything we're doing is with a cylinder that's got a fixed number, N doesn't change. But if we look at PV equals NKT, and we allow N to change, right, what happens? Well, that's how you can make a hot air balloon, right? So I'll just do it for fun real quick, without burning myself. Oh my goodness, maybe I will burn myself. See, can I do this? So a hot air balloon, how does that work? Hot air balloon works by, let's see if I can avoid burning this thing. All right, I don't have my fire extinguisher today. This may be a risky move. But the idea with a hot air balloon is that if you heat up the gas inside the balloon, right, well, P equals NKT, well, P is a constant, right? The pressure in the room is 1 atmosphere, and the pressure inside the bag is 1 atmosphere. So what changes? The temperature inside is bigger. Pressure is the same. The volume of the bag is the same as it was before, right? I didn't change the volume of the, well, that's not, you see, that's puffed out now, okay, fine. So the puffed out volume of the bag is the same before and after. But the number of particles has changed. Are there more particles inside there or fewer if P equals NKT and I let T go up? Does that make sense what I'm asking? Yeah, say it again. Higher T, but P is the same, V is the same. So what happens to N? Does it go up or down? It goes down. N has to go down. And if N is down inside the bag, is the density inside the bag bigger or smaller? Smaller. So it should go up. It should just be a buoyant force on a hot air balloon, right? Let's see. Oh, I didn't get very far. Oh, no. Oh. All right, there it is. And the main thing was I did not light it on fire. That's what happens. That's when that demo goes south. That's what happens. Anyway, good. All right. So I'm going to put this over here and get out of your way now. So that's good. So you should be able to think about P equals NKT in a more general context than just PD diagrams, right? But when you've got PD diagrams, N is fixed. So it's just some number, that stays the same throughout the problem. Okay, great. So let's think about the Carnot cycle. What does the Carnot cycle look? Oh, yes. The number of particles went down because I heated up the gas inside. So the volume is the same, so it has to push these particles out. Like suppose I had a closed bag and I heated it up. What happens then? And the bag can't change its volume, and the particles can't escape. Then the pressure goes up. But if I have a big, huge hole in the bottom of the bag, then the pressure is, it's in contact with the atmosphere in the room, and air molecules can go in and out. So the pressure inside doesn't actually go up. The air molecules escape. Well, if they're escaping, and if more are coming out than are going in, then the number of molecules in the bag goes down. And that's why hot air balloons rise, because they have fewer molecules inside compared to the number of molecules you would have had in an equivalent volume of air that's at the same temperature as the outside air, right? Yeah. So, yeah, in other words, it has a buoyant force, because the pressure below is a little bit bigger than the pressure above. Right? And that difference results in a buoyant force that's bigger than the buoyant force in that case is larger than its gravitational force. Even if you include the mass of the little piece of plastic, the little bit of mass there, it overcomes that. Right? Anyway, all right, great. So what's the Carnot cycle? The Carnot cycle is just a specific cycle that allows you to calculate the thing we really care about when we build engines. The thing we care about is the efficiency. And I'll probably just draw this, talk about it a little bit, show you some more demos, and we'll go into this even more next time. But the bottom line is Carnot cycle uses the two nastiest curves that we've got. Why don't they make a square Carnot cycle? It's a lot easier. But what they usually do, in thermodynamics, what we do is we talk about isotherms, and we talk about these adiabatic type curves, these constant Q curves, these Q equals 0 curves, right? So here's the Carnot cycle. It moves around like this. Turns out to be convenient, even though it seems like it's the hardest thing to think about. And so let's call this point 1, point 2, point 3, point 4, right? This is a PV diagram, right? It's an ideal gas going around. And when we ask, okay, what's going on? Well, during this part of it's going clockwise, so it's an engine, not a refrigerator, engine. Clockwise. What's going on during these vertical parts, not vertical, but more vertical parts? These are these constant Q curves. No heat is being exchanged. There's no heat exchange, or whatever. Q in equals 0 along here, right? Q in over here equals 0. Now, because these things aren't perfectly vertical, there is some work. There is area under the curve. It turns out, though, that the work done over here equals the work done over there. And you can do the math and calculate that and everything. And you see it's in opposite direction. It goes to the right over here and then left over here. So the work that you do on the system here equals the work it does on you over here. It's a wash. Right? You don't get anything out of that. That's not why your engine's doing any favors when you run it and burn gas. Why do you burn gas? Burning gas is where the heat comes from. That's where you get Q. And you say, wait a minute, there's no exchange here. Yeah, but there is exchange up here and down here. So what you want to do is add heat to the engine in one part of the cycle and take heat out in a different part of the cycle. And you want this to happen at different temperatures. That's the crucial fact. That up here, heat is going in. So we call this, the book calls this Q, the book uses Q sub H for Q hot for the heat exchange during the hot part. We're going to call that T hot. And then this over here is for T cold. Remember, these are isotherms. This temperature along this curve is the same everywhere. T hot, some high temperature. Over here, it's some low temperature, T cold, right? And then we're going to say, all right, there's some heat that goes in up here, and there's some heat that comes out over here. Cold, hot. And I'm trying to use the book's sort of view. They have positive numbers for their QC and their QH, but they don't have ins and outs on them. So I'm saying, okay, let's call it Q out C, and that's a positive number. That's the heat that came out from point 3 to point 4, out of the ideal gas. And Q in, that's the positive amount of heat that you had to add from point 1 to point 2. Now, if no, let's see. How far should I go with this? So if we want to calculate what the efficiency of this engine is, so what is efficiency? Well, efficiency is going to be equal to the net work. I mean, really explicit. I wish the book were more explicit, but the net work for the whole cycle. And let's do work by, right? Because what we want is we don't know how efficient our engine is. I want to say, what does I want from the engine? I want to get work out of it. That's work by the engine. Work by, and it's net for one cycle. So I just wrote net to mean the whole cycle. You can also, I'll write that cycle. All right. And what are we dividing by? We're dividing by the thing I had to pay for. I had to pay for gas, gasoline. And that gasoline provides Q in, but only on the hot side. You might think, well, wait a minute, why do you have, so this includes both the work done, this includes the work done in all 4 segments of the cycle. But this only involves heat that's being exchanged in one part of the cycle. Why do we do that? So if you go to the gas station and say, no, I paid $15, actually probably like $50 for my gas last week, then I got all this heat out of my exhaust pipe. I'd like some of my money back. Here's the hot exhaust for you, right? They will not give you any money for that hot exhaust, even though you could provide back to them some of the heat you got, right? It's waste heat that came out of your car. It didn't result in your car moving further. Your car's not, efficiency is not going to transfer 100%, I mean 1. It's going to equal something less than 1. Even for this Carnot cycle, which is ideal, right? Your car's not even anywhere near as good as that. I'm sorry to say, well, at least mine isn't. My car isn't as good as your car. But your car is nowhere near as good either. For a lot of practical reasons. In fact, I can ask you, like, why is there energy crisis in the first place? Energy's conserved, right? You can't get rid of energy if you try. So how is it that we have to pay for gas and mine it out of the ground? Why can't we just preserve all the energy we've already had? Well, it turns out there's different kinds of energy, and as I said in the beginning, work and heat are really intrinsically different in terms of what they can do for you. And this efficiency, which I'm not going to go through this thing today. I'm going to do it next time. I'm going to talk a little more about engines in practical terms. But I want you to think about this. This is a good thing to understand. No matter what the calculations turn out to be, why this is the right thing to calculate. Like, why are we calculating this? It turns out that if you exchange heat, you wind up changing the number of, when heat is added to a system, the number of available states in the system changes. Its entropy changes. And if that's accompanied by a decrease in something else's entropy, that's okay. You can make it reversible. You can get it back. But when you burn gas and use that heat to make your engine run, and take some fraction of the energy you got from the heated up gas from and by gas now I mean like actual gas, not gasoline. You take that petroleum, right? You burn it, and you get some heated gas, a heated non-solid, non-liquid gas, right? Heat it up and expanding it, and then expands the cylinder and does work. It pushes the piston down. You get some useful work out of that, but then you also get some wasted heat that comes out, and it's inevitable. You can't avoid that. And you're limited by the temperatures that you're able to work at. If you could actually work at absolute zero, if you could have a cold heat bath that is at 0 Kelvin, right, as part of your car, and it had so much heat capacity, you could take as much heat as you wanted to give it, and it wouldn't change the temperature, then you could run it perfectly 100% efficiency in principle, right? But that's not the way it works. What we do is we start off at room temperature, which is already at, 300 Kelvin, right? Unless you live in very cold parts of the US, but then it's not that much different. Still way up in the hundreds of Kelvin. And then you burn some gas that gives you a hot reservoir, gives you some heat. Well, the flow of heat from the hot to the cold reservoirs, that does give you, it allows you to make an engine like this, but it's not going to give you 100% efficiency. Well, I'll tell you what, I'll go ahead and work it out real quick and just tell you what this turns out to be. And we'll probably do it a little more next time. We know that along the, if you accept my statement that these two cancel out in terms of the work, we just say, well, how much work is being done at the top and the bottom? Well, these are isotherms. These are constant temperature curves. That means the amount of work you get out is equal to the heat you put in. However much heat you put into the system here equaled work out. However much heat came out of here was work you had to put in. It did work to compress the gas, and while that's happening, heat's coming out, and they're equal. So that means that I can write all this in terms of the Q's. The net amount of work you get out is going to be Q hot minus Q low, cold. And if you divide that by, and these are all ins. These are all, excuse me, they're not all ins. This is in, this is out, and this is an in. Oh man. And the reason I did it that way is to make all these positive numbers. All these things are positive numbers. Okay? We figured that out because we're just looking at these parts of the curve. You've accepted from me that the work here cancels for these two, and these guys, and the heat exchange equals the work done in those two cases because they're isotherms. The energy didn't change. It has to be that work in equals heat out and vice versa. And so then we say, well, okay, how do we write this? Well, this is just equal to 1 minus QC out over QH in. So what does that tell us? It tells us that the efficiency is at most equal to 1. But in fact, if you don't have a heat, this is the thing I just said in words a few minutes ago. Well, actually, not yet. I have one more step to get to where I got a minute ago. The heat exchange on the cold side is a loss for you, right? That's something that you paid for that you didn't get useful work out. So you want to minimize how much heat comes out at the bottom. Well, we know from our equations over here for isotherms that Q high in equals NKT, right, times the log of the ratio of the volume. So I have it in terms of layers. It's 2 over 1, I think. I've got my numbering right, so it's AB. I think that's right, yes. Okay? Well, if you do this, and the same thing's true down here for Q cold. If you put all this stuff together, and if you do you trick around, you figure out exactly how to think about the ratio of V2 over V1 and the ratio of V3 over V4, when all the dust settles, a miracle occurs, right? You go through all the math. What do you get? You get that the efficiency is actually equal to 1 minus TC, T cold over T hot. And by that I mean the temperature of the heat bath with which you're exchanging heat up here, that's T hot, and the heat bath down here. After all, how would you achieve this? Forget your engine in the car, it's a complicated device. How would you achieve this with a piston and a heat bath? What you would do is when you want to move along here, you'd put the piston in contact with your heat bath. So here's your heat bath, it's T hot, you put your piston right there, and you would expand it. You would raise this up. That's how you go from 1 to 2, right? So this is going up. And you're expanding the gas in contact, and you do it slowly. So that means that heat goes in, Q in, right? That's what it is. And then what do you do during this part? You just expand it, you keep pulling it, but you do it out of contact. right? So you're still expanding, you're still raising up this thing, it's expanding the volume, but now you have insulation all around it. It's Dow-Corning insulation, and it's not touching any heat path, and so on. That's how you do these things. In contact with a heat path, insulation, in contact with a heat path, now you put it back in contact with a heat path and you compress it, but it's in contact with a cold heat path, one that's matched to the temperature that you got to when you expanded the gas, and so on. And then you go back here and you go back to the top. So this allows us to go through this calculation, which I just sort of skipped through and gave you a couple highlights. I didn't really show you fully how you do it. The book goes through it in more gory detail. But this is the result. This is an important result, even if you don't know all the details of how you got it. And it tells you that if you don't have a super cold heat bath to put on the cold end of that cycle, right, then you have to have some waste heat come out. You can't avoid it. It's a fundamental law it's one of the most fundamental statements about anything humans know about the world. And the result of that is that's why we have an energy crisis. You can't just exchange energy back and forth and be able to keep using it. The quality of energy goes down with time. So what I'm going to do right now is show you, I'm going to talk more about that next time, but I want to show you right now just a cutaway of, I took this out of my own car right here as a little piston, and I'm going to move this thing up and down and show you sort of what goes on. So if you have a 4-stroke engine, what does that mean? You have cylinders going, well, first of all, it's V8 and all that. So the number of cylinders in your car, this thing's a cylinder, right, is the 8 and the 4 and the 6 and all that stuff. But my car's working. I have 4 cylinders. They're all simultaneously moving and being useful. And I've got a regular car like most, so I don't have a diesel engine, so that means that I actually have a spark plug. So if you don't have spark plugs in your car, you have a diesel engine. Those kind of engines work by just compressing the gas. You saw me do it a minute ago with that piston. I compressed the piston and then a piece of paper ignited spontaneously. That's how diesel engines work. If you compress them fast, no need for a spark plug. It just ignites spontaneously once you reach the flash point, if you like, if that's the right term, for the diesel fuel. And you need a special kind of fuel for this, and et cetera, et cetera. So what's the cycle the car goes through? So let's just think about this. We just compressed the gas, and there's both, and by gas, what do I mean? I mean that there's vaporized hydrocarbons in there, whatever it is, high octane fuel, whatever I drive with, and then there's also oxygen, O2, and there's nitrogen too, but that doesn't, whatever. That just provides gas that gets, well, I think it's important to expand. Okay, so you got your nitrogen and oxygen. Oxidation occurs when this light goes on, the spark plug lights it up. Now there's an explosion, and the result is that there's a bunch of hot gas in here now. It's also true you have more gas molecules because you broke up that big molecule with hydrogens and carbons on it into smaller pieces of CO2 and all that stuff. But let's forget that part. That does play a part, but that's actually not the main thing that's happening. The main thing that's happening is you're adding heat. You're taking a bunch of chemical energy and you're converting it into thermal energy of the gas molecules. Those gas molecules now are really hot, right? As a result, P equals NKT. Well, the volume didn't change yet, but the pressure sure did. Pressure went way up. So now when it goes down, positive work is being done by the gas on the piston. It's doing work. It's helping you out, moving your car forward. Now when it gets to the bottom, a little valve opens so that when the thing comes back up, it's because of momentum, right? Because there's angular momentum on this, which won't be on the funnel. But there's angular momentum over here that spins around, makes this guy keep moving, and then a valve opens up, and then gas can escape. All that gas escapes. Now when it goes back down again through this momentum, the angular momentum, it's sucking in oxygen and more fuel, right? And now the valve closes at the bottom, and the 4th stroke is where it compresses that mixture and prepares for the next ignition. So that's why you have 4 strokes. It goes all this stuff. The Carnot cycle doesn't exactly mimic what's happening in your engine. But that's okay, because any possible cycle I can draw on a PV diagram, I can break up into little tiny Carnot cycles and make whatever shape I want around the outer boundary. So when we learn about efficiency, that really does tell us about any type of cycle your car might have. It turns out your car's not as efficient as the Carnot cycle says. In fact, Carnot is like car not. It's pretty reasonable. Cars are not as efficient as Carnot cycle, right? I'm sorry to say. If it were, you could save a lot of money and be good for the national security too. Anyway, I know, awful joke. People hate that. Anyway, we'll do more of this next time, and we'll talk about entropy. We'll have the second law of thermodynamics.